we learn about case number 1 for constructing a heap, which will take n log n running time. And we would like to improve it whenever possible, so that will be what case number 2 is about. So for case number 2, the list of entries that we want to insert into the heap is known in advance. So that means we will be able to process maybe the input list at one go. That's something we'll see exactly how we can do it for case number 2. And we'll argue ultimately the running time for case number 2, so-called bottom-up heap construction, will take only bigger of n linear time. So you can think about linear time is definitely much more efficient than the n log n in case number 1. That's something you want to keep in mind first. And as before, we have one slide containing the principles that you really need to follow algorithmically if you want to implement it in Java, and also how you can do the visual illustration. And I'll try to show you step by step, and then after each step presentation, I'll try to switch to the visual illustration right away, so you can kind of follow when you actually do your own study. The problem is we want to build a heap out of n entries. So this part here is identical to what we had earlier for the case number 1, the top-down approach. But the implicit assumption right now is different. We can be supplied with the list of entries all at once rather than one at a time, right? Notice the implicit assumption we are making. And I got several steps over here. Let's show one by one. Step number 1. Oh, before that, let's talk about some additional assumption. In addition to that, all the entries are supplied all at once, we got some additional assumption that we want to understand. The resulting heap will be completely filled at all levels. So that's just easier for us to actually show you the different steps. Also, I'm going to show you some mathematical pattern that you can also study more carefully beyond the lecture. Right, so this is our additional assumption over here. We simply say the number of entries will be exactly equal to 2 to the power of the height of the tree plus 1, and then minus 1. And I will try to plug in the numbers once we see the concrete example to see why this will be the case. But for you, your mental exercise will be think about why this number over here should be the case in order to get a full binary tree. Right? Remember, heap is actually a complete binary tree for sure. That's satisfying the structure property. But what I'm putting over here is I'm assuming that whatever heap we're going to build ultimately is going to be a full binary tree. Of course, at the same time, you'll be a complete binary tree as well. That's some mathematical property you want to think it through. Of course, reach out to me if you got any trouble. Alrighty, so let's now talk about step number 1 for the so-called bottom-up heap construction. Meaning that we're going to build from the leaf nodes first and then go gradually up to the root. That's why it's called bottom-up. Step number 1. We want to treat the first this many number of list entries as the heap roots, number 1. And let's just go over that. And then that means we got this many heaps with height 0 and size 2 to the power of 1 minus 1, which is 1, constructed. That'll be step number 1. Let's see exactly how this can be visualized. And one thing I'm going to point out as well on the iPad, you want to notice more about the step index over here, which can be 1, can be 2, can be 3, all the way to step h plus 1, as you will see. And also notice the exponents over here, 2 to the power of something over here. Right? I kind of listed explicitly because you will see that the pattern of the steps nicely correspond to the exponent for the 2, for the number over here, the denominator over here. And also you can see here is also 2 to the power of 1. You will see that the exponent over here is actually going to increase as we go to the later step. So when we go to step number 2, for example, the exponent over here for the 3 occurrences over here, they will all be increased to 2 for the step number 2. Right? That's something look ahead I want to mention. The steps have been laid out very carefully, so that's why that means you have to study them carefully and precisely as well. Let's visualize step number 1. Right? So step number 1 is over here that we just spoke about, right? And let me just highlight one thing over here. You can see the 1 over here is really corresponding to the 1 over here, the 1 over here, and also 1 over here, right? And how many nodes do we have? For our concrete example, ultimately we want to build 15 nodes in total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 in total. Let's plug in a number right away. Ultimately, the n, let me use the same color, n over here is going to be 15, right? This will be our example. And then the first n plus 1 divided by 2 to the power of 1. What would that be? 15 plus 1, 16, divided by 2 will be 8. So the first number over here will be just 8. That means we're going to build 8 heaps of size 1, 2 to the power of 1 minus 1 will be 1, and also each of the 8 heaps, they have height 0. That's exactly what's going to happen. Let's now put down the consequence for the first step. So let me just put step number 1. Step number 1, we're going to get the first 8 entries in the list. 1, 2, 3, 4, 5, 6, 7, 8. Over here. That's what we're going to get. And in that way, we're going to get 16 and also 15 and then 4, 12, 6, 7, 23, and 20. Right? So here we got 8 heaps with the size simply just 1. Remember we said the smallest heap you can get is a 1-node heap, in which case you only got a root. 1, 2, 3, 4, 5, 6, 7, 8. We got 8 heaps. And also the height will just be 0. Right? You can see each of the heaps only got 1 external node in the tree. In that case, the height will just be, by definition, 0. Let me also highlight 8 heaps we have just constructed from step number 1. 1, 2, 3, 4, 5, 6, 7, and 8. And let's now move on to step number 2. And we'll read it together. Step number 2. I don't need to go back to the slide because the page is simply a screenshot from your slides. Step number 2, you can see the 2 over here is now going to correspond to the exponent over here. You can see the 2 here, and also the 2 over here, and also the 2 over here. And what will be the next entries to grab from the list, from the input list? It will be n plus 1 divided by 2 to the power of 2. N is 15. 15 plus 1, 16, divided by 2 to the power of 2, we will get 4. Right? If you try to evaluate the value over here, so this part here is actually going to be 4. One thing you may have noticed already, to really use the bottom-up construction mechanism, the first step is going to involve the most number of entries, in this case about half of the list, and then we go for about 1/4 of the list, which will take about here, and the next one will be 1/8 of the list, and then eventually you will get to the root, which will be just 1 element. That's one insight you can observe as well. Alright, so let's now talk about it. And each root is going to set the 2 heaps from step number 1 as its left subtree and right subtree. I'll show you to in a moment. And also we're going to perform down heap bobbling. Right? You can think about what we're doing is we are setting the root for each of the heaps from the previous step. It will be as if we just finished the deletion process, in which case we're going to do the down heap bobbling. That's something we'll see as well. And the result is we're going to generate how many heaps? We're going to generate exactly 4 heaps in total. And then each one of them will be of height 1, and also size will be exactly 3. We'll see that. You can see this one here from the earlier one. The size will be 1. As you can see, they're all 1-node heap. And after the second step, we're going to get 2 to the power of 2. So that will be 3. Right, let's now do step number 2. For step number 2, what we can do is, let me just copy what we got from step number 1. 15, 4, 12, 6, 7, 23, and 20. And the next set of elements from the input list will be the next 4, right? As we said earlier, that should be the 4, according to the step over here. That'll be 25, 9, 11, and 17. So let me put it out. So it's 25, and then 11, and then 17. Oh, 25, 9. Sorry, I missed the middle number. So 25, and then followed by 9, followed by 11, followed by 17. And we're going to simply set it as the left subtree and right subtree, right? Left subtree, right subtree, and etc. And after these, we should really try to fix the heap order property individually if necessary. For example, if you look at this will be the parent, this will be the child, right? You can see 25, is it smaller than or equal to this and this? Well, we'll put it another way. Let's put it in the way that we are familiar with. 16 larger than or equal to 25 is not the case. So we have to fix it, right? In that case, how do we fix it? We have to choose basically the smaller child. 25 and also what will be the smaller child? 16 versus 15. That will be the 15 will be the smaller child. We're going to choose it, and then we have to swap it, because you can see 15 larger than or equal to 25 is not the case. So that's why we're going to do a down heap bubbling, just one step. So what's going to happen is we're going to swap these two. So this will be 25, this will be 15. And the resulting tree over here is guaranteed to be a heap after the down heap bubbling. Right, let's now do the next one. And for the next one over here is that a heap? It is not, because 4, for example, 4 larger than or equal to 9 is not the case. So it's violating the relational property. So we're going to think about parents, and what should be the child? We want to choose a smaller one. Smaller one would be exactly 4 over here, and then we're going to swap them, because 4 larger than or equal to 9 is actually not the case. So we're going to swap them. So we got 4 here, and we got 9 here. And this one here, parents, and the smaller child is this. 6 larger than or equal to 11 is also false. So we're going to swap them. So swap them. So that will be 11 and also 6. Finally, if you take a look, 17 and smaller child is 20 over here. 20 larger than or equal to 17 is actually true. So this one here is already a heap, so we don't need to touch it. And let's now double check the number. How many heaps have we got so far? We got the first heap will be 1, 2, and 3. The second heap, 1, 2, and 3. Third heap, oh, beg your pardon. The second heap should be 12 over here. The third heap, 1, 2, and 3. The fourth heap, 1, 2, and heap. How many heaps in total? 1, 2, 3, and also 4. So that's exactly the 4 over here, right? That's the number. 4 heaps. What will be the size for each one of them? It should be 1, 2, 3, and also 1, 2, 3, and etc. What about their heights? It will be exactly just 1, right? You can see from the maximum depth from the child nodes. That'll be 1. Right? So far you can see it's very logical. We're just following the steps faithfully. And over here, I don't really have step number 3, but you kind of see the pattern already. Right? Let me do one more step without the description over here. But the final one over here is actually going to be very important, which I'll get into. That'll be the terminating step. For step number 3, what should we do? And let me see if I can just move this one here a little bit upwards, so I can leave more space for the next 2 steps. That should be good. Let's talk about step number 3. And for step number 3, let's put down the heaps that we got so far. So what we got is, we got 15, 16, and then 25. We got 4, 9, 12. And here we got 6, 11, and 7. And we got 17, 23, and then 20. Agree? And what will be the number of entries we should really extract from the input list? And we can do a little bit of pattern derivation over here. So you can think about step number 3. Okay, over here we can just do some derivation. And how many entries? The number of entries we should really extract would be n plus 1 divided by 2 to the power of the step number, which 2 to the power of 3. And this one here is actually going to give us 15 plus 1 will be 16 divided by 8, that'll be 2. So we only need to grab 2 more entries, which I'm going to show in orange. 2 more entries, only 5 and 8, right? And then we're actually going to put, let's say, 5 over here and 8 over here. And we're going to set the children Oh, you know what? Why don't I just give maybe different color so you can see? So we got 5 over here, and also 8 over here. This one here, this one here, this one here, and this one here. Right? That's exactly about the left subtree and right subtree over here. This one here. And let's now fix the heap property. Okay. What we can do is let's now start with the root over here. 5 compare with well, think about 5 here, and what's the smaller child? The smaller child is actually 4. 4 larger than or equal to 5 is actually false, right? So that means we're going to swap these two. So 4 here and 5 over here. And 5 here, what's the smaller child? 9. 9 larger than or equal to 5 is actually true. That's it. And you can double check by yourself that this is a heap itself. What about this one over here? Let's see. The root is 8. Smaller child is 6. 6 larger than or equal to 8 is actually false. Swap these two. 6 here and 8 over here. And what about 8? What will be the smaller child? 7. 7 larger than or equal to 8? False. Swap them. That'll be 8 over here. 8 over here. And 7 over here. So ultimately, this will be the heap that we got. So we got 4, 15, 16, 25, 5, 9, 12. And 6, 7, 11, 8, 17, 23, and 20. Right? We can just do a little bit more derivation for step number 3. We just talk about the number of entries. What about the size of each heap? By the way, we have built exactly 2 heaps out of step number 3. This will be heap number 1. This will be heap number 2. What will be the size for each heap? According to the formula, it should be 2 to the power of the step number minus 1. So 2 to the power of 3 minus 1, which is equal to 7. And that one there also nicely corresponds to what we see. You can see the size 1, 2, 3, 4, 5, 6, 7. Similarly, 1, 2, 3, 4, 5, 6, 7. Also true. What will be the height for each heap? Well, according to our pattern earlier, you can see in the case of step number 1, the height is actually 0. And step number 2, the height is actually equal to 1. Right? You can see that should be the step number minus 1. Right? That's really the pattern that's really can be inferred from the conceptual sketch. So number 3, the height of each heap from step number 3. It should be exactly equal to the step number 3 minus 1. Should be 2. And let's double check if that's the case. For example, for this heap over here, you can see the child with the maximum depth over here got 1 and 2. So the height is actually 2. So that's correct. So that'll be step number 3. And for our example over here, we are basically have completed the second last step. So the final step over here will be to really get this 14 as the root. That's what we'll do. And that one there really corresponds to the step h plus 1. Right? So the dot 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 over here can be for other examples where the tree is actually taller. Right? I'll leave that exercise to you. But let's now talk about the final step over here. The final step will nicely correspond to exactly what we got for the 14, the last entry. Let's now talk about step number 4. Right? The final step from which we're going to result in just a single heap. But let's see exactly how. So we're going to treat the next, right? So this one will be interesting over here, right? So this one over here is going to be m plus 1, which will be 16, divided by what will be the height of the tree. You can think about current, up to now, we got 1 and 2. The height is actually 2. We want to add another node on top. So that means the height is going to become 3. So ultimately, our tree that's being built, our heap that's being built, has the heights. Now we can actually put it in. The height would be actually 3, ultimately. Right? So what we can think about is, here, if we plug in a number, 2 to the power of h plus 1. So 2 to the power of 3 plus 1. So that will be exactly equal to 1. Right? You can see the nice precision about math. So 16 divided by 16 will be 1. So that means we want to grab just one more entry from the list, which will effectively exhaust everything we are given in the input list. Right? So that's number 1 to note. And we'll talk about exactly the size and also how many heaps and also the height a little bit later. Let's see how we can do that. So grab 14 over here, which will be the final root. And for that one, let me use a different color over here. How about 14? This will be the ultimate root that we want to introduce. And for that one there, we're going to put 14 on the top. And then we got 2 previous heaps. One here and also one over here. And we want to link them to be the left and right subtrees for the 14. Right? Let me now copy that carefully. And the first one here is 4. Underneath, we got 15 and also 5. And 16 and 25. And over here, we got 9 and 12. And the right subtree, we got 6 over here. Underneath it, we got 7 and also 17. And underneath it, we got 11 and 8. And then we got 23 and 20. Think about this part over here corresponds to this tree. That's from step number 3. This part over here corresponds to the heap. That's from step number 3. Right? And that's the new entry we just got. And we're going to fix the relational property if it is violated. Let's see. So 14 here, smaller child will be 4. 4 larger than or equal to 14 is actually false. So we're going to swap them. So we got 4 here and 14 over here. And then smaller child for 14 is actually 5, right? 5 larger than or equal to 14 is actually false. Swap them. So this will be 14 and this will be 5. And 14 got 2 child nodes over here. The smaller one is 9. 9 larger than or equal to 14 is actually false. So we have to swap them. So we got 9 here and 14 over here. That will be the final heap, final one. Let's now take a look at some numbers over here. The first one we want to check, how many heaps have we got in total? Just one heap, right? That's a number we just calculated. Every heap has the height h, which will be exactly 3. For example, well, just only one heap. You can see the height will be 1, 2, and 3. The child node with the maximum depth. What about the size for the heap? It will be exactly this. Well, that one corresponds to the geometric sum about the nodes from different levels. But we can calculate it just to confirm. This one over here will be 2 to the power of h plus 1. So that will be 2 to the power of 3 plus 1 minus 1. You will get exactly 15. So we got 15 nodes. You can definitely double check. We got 15 nodes over here. That will be the bottom-up heap construction that I tried to demonstrate to you. It's very thorough, and you want to make sure you know how to do it. And of course, the number of entries may not be exactly corresponding to this particular assumption over here. So in which case, you have to do some minor adjustment. For that one, I'm going to leave to you for the implementation. But this nice little assumption over here just make it easier to illustrate the principle. Hopefully you have learned that already. So you definitely want to make sure I understand how I illustrated the bottom-up heap construction mechanism, and you want to do it from scratch on a piece of paper on your own. Let's now talk about the running time. Why would that be bigger of n? And I think for this to really argue about the running time for the bottom-up construction, bottom-up heap construction, we don't really have to go into the very formal proofs about it. You can definitely maybe do some little bit of research. It's definitely very well known about how to justify it. But I just want to give you some intuition, right? And that's really some insight I already mentioned when I actually follow the steps. Let me just talk about it. And this will be the exercise I wanted you to do, but I already did it together with you. The insight will be you want to make sure you understand that for the very first step, that one there is going to handle half of the entries already. And the next one will be 1/4, 1/8, and also 1/16 of the node, right? You can think about you're going to handle just fewer and fewer nodes after as you progress through later steps. But the first step is going to handle already half. And think about the running time for the first step. The first step over here is pretty simple. right? You can see there's really no computational complexity over here. You're just choosing the half of the nodes over here, and then they are automatically heaps by definition. Even for step number 2, to really do the bottom up, to do the top down heap bobbling, the down heap bobbling. Even that, you can see the height of the tree is only 1. So for each of the fixes we did, it's also very cheap, right? That's something we also argued earlier for the top-down heap construction, right? So you can see after step number 1, after step number 2. Let me just put it down over here. For step number 1, we handle just about 50% of the nodes. Agree? About half. About half over here. And then 25%, and then about 12.5%, and etc. This will be about 25%, about another half. 25% of the nodes out of the 75 nodes that are already in the entry list over here. They can be handled rather straightforwardly without much cost. Especially for this one, you can see the height is only just 1 over here. And of course, even for this one here, the height is only 2. And after another 12.5% of the nodes, you can see we have handled most of the nodes already, more than 50%, way more than that. So that's kind of the intuition you can really get. For the bottom-up heap construction, you can really handle most of the nodes in a very efficient way. It's mainly the maybe last few, or maybe the last one in this case, that when you actually construct the overall heap over here, you have to do the top-down or downward heap bobbling to really fix the relational property for the heap. But that one there is only going to be log n. So overall, you can think about you're just going to touch every node just once, in which case it's going to be big O of n. Right, it's a very informal justification over here, but you can definitely refer to what I wrote on the slides over here. That's the example we just went over, and that's really about the percentage I just mentioned. Right, you can think about we have handled 50%, 25%, 12.5%. Just the first 3 steps alone already handled about 87.5 of the nodes already. So for the rest, it's simply going to be, even though they might be costing more, but very few nodes that you have to handle already. And finally, it's going to be big O of n. So this is a number you can take for granted, but I would suggest also try to understand about the intuition I just mentioned to you. Right? For formal proofs, you can definitely do your own research about how to prove it, but I can tell you it's a linear time. So should you choose top-down or bottom-up? I would say if you already got a list of entries already, you definitely should really go for the bottom-up approach, because that one is going to be cheaper, linear versus n log n. But if you really have no choice, you're only given one entry at a time. In that case, you have no choice but choosing the top-down approach, which will give you n log n performance. Alrighty, so that's about the 2 cases of heap construction. You want to make sure you understand each one of them. I really went very thoroughly with you about the various steps, and also for the bottom-up approach, I will highly recommend for you to really understand about this slide over here of the principle, especially to see the formal pattern of constructing the heaps. That will definitely help you if you actually want to put this conceptual sketch into Java implementation.